Hi, everyone. We'll give it just 1 minute for everyone to turn into the Zoom. And tell that lots of people saw the Discord announcement. Today is Kira's birthday. So thanks for the really sweet messages. We'll make sure that they get back to her. Just a few quick announcements before I hand over the lecture to Amir. Gabby, if you want to go ahead, or Amir, sorry, if you want to go ahead with the slides. Cool. Hey, everyone. So just a reminder, my name's Rachel. We just wanted to remind you all that it's really, really important to check Canvas. You should have received an email yesterday with this as a reminder. We had many questions this week being emailed to us that were already answered on Canvas. So please make sure you have access. If you don't, there's a tech form that you can fill out, and we will make sure you get the access that you need. You can play around with the notification settings and you can set it up so every time we post an announcement, it gets emailed to you, if that's easier than having to remember to regularly check your Canvas account. So please do that. If you still can't find your lab link, which we got lots of emails about, well, hopefully you did, because labs happened last week and attendance is mandatory as a reminder. But if you didn't find it, it is posted as an announcement in your Canvas lab section. So please check on that. And then just lastly, a reminder that regular homework is starting this week. So there's an assignment that will be tied to the lecture that Amir gives today in the lab sections that Akshay has designed for this week. So remember, those assignments are due every Sunday at 11:59 p.m. And so make sure you make time in your week, in your schedule, to get that assignment done this week. And that's all from me. If you have any questions, please email student@qubitbyqubit.org. But otherwise, I'll hand it over to Amir for his first lecture of second semester, and he'll start with a quick introduction.
Thanks, Rachel. Hi, everyone. My name is Amir. I'm a third-year doctoral student at MIT in quantum computing, and I've been working on quantum computing since a few weeks after I turned 18. So for all of my adult life, almost. I've been teaching a quantum computing course at MIT since 2017 aimed at undergrads, and I've been working with the coding school and the Qubit by Qubit program since this past summer. My research is focused on experimental quantum computing using superconducting qubits currently, and before that, I used to work on nitrogen vacancy centers in Diamond, which could be used as quantum memory. So with that, let's dive right in. But before, today is Michelle Obama's birthday, which Michelle Obama, for those of you who don't know, was the former First Lady of the United States. But more importantly, it's Kira's birthday. So make sure to wish Kira a happy birthday on Discord. And again, we want to wish Kira a happy birthday on behalf of the Qubit by Qubit team. Okay, so now that that's out of the way, let's dive right in. Over the course of the next 3 lectures, we'll be talking about quantum mechanics. This lecture, we're more focused on the concepts and the principles of quantum mechanics. Namely, what is quantum and how do things behave on the quantum scale? We're going to talk about why we need to know that and where that comes into play when we're thinking about quantum computing. But the quantum part of quantum computing should already be enough motivation for us to learn a little bit of quantum mechanics. Then the next lecture, we're going to talk about quantum 2-level systems, which is essentially what the qubits are and what happens when we measure a qubit or 2-level system. In the third lecture of this series, we talk about the postulates of quantum mechanics, and postulates is just a fancy term for rules. So with that, the objectives of this lecture are to understand why we need to know basic quantum mechanics for quantum computing. And then to understand the pre-quantum era thinking about particles and waves. So all of us almost have some intuitive notion for what particles are and what waves are. But something that we're interested in is how do particles and waves behave when we add quantum mechanics to the mix. And for that, we want to understand how particles behave as waves and how waves behave as particles. And finally, we want to understand how the path of an electron can be described mathematically. And again, electron being a object that we're somewhat familiar with, then that everything about it is almost governed by the rules of quantum mechanics. So let's start by talking about what does quantum mean. So I think the first significance that I want to bring up about the quantum world versus the classical world is that in the classical world, the assumption that we have is that things around us are continuous, meaning that if I can be in two positions, let's say in a position A and position B, I can also be in a position in between the two. Whereas in quantum mechanics, actually, nature behaves in a discrete way. So if I can be on step 1 and step 2, I can't be actually stepping anywhere in between. So I think this visual does a good job of conveying that message. In the classical world, things are continuous, whereas in the quantum world, nature acts discretely. And we're going to see this in action soon. So what does quantum mechanics do exactly? Quantum mechanics describes how objects behave at small scales. So again, describes the physics at the microscopic level, and again, it could be extended to macroscopic level or like phenomenon that we actually see in everyday life. But the major discrepancy between quantum physics and classical physics comes again when we're viewing objects at a small scale. And it's seemingly incompatible with the types of observations that we make in everyday life. And because of that, some concepts from quantum mechanics are unintuitive, since it's not something that we've grown up seeing around us. But they do play a role in intuitive concepts that we see around us. That leads to counterintuitive effects, things that we're not used to necessarily based on our daily experience. And it can be used for describing the behavior of an atom. So, for example, the path of an electron around an atom is described by quantum mechanics. Prior to developing quantum mechanics, scientists, physicists especially, were trying to describe how an atom behaves using the classical laws of physics, again, either Newtonian mechanics or electricity and magnetism. But there was always something missing. There would be something absent from the picture that would lead to an atom being unstable for some reason. But now, after we discovered quantum mechanics, we were able to exactly explain how an atom behaves. So now let's talk a little bit about quantum computing and where does quantum mechanics actually play a role. So quantum computing, which is what we're interested in studying in this course, uses quantum phenomena to perform computation. And in this case, quantum mechanics is a tool used by our quantum computer or computer to solve certain computational problems that normal computers cannot, because they're lacking the resources, these quantum mechanical resources. So let's review what these resources are. And we've talked about this extensively in the first semester, but we're going to review them real quick. So the first one is superposition, where objects can be in two places at once, or to translate it to terms that we'll be using throughout the course, is that the quantum object, can be in two states at once. So for example, a classical bit can either be 0 or 1, whereas a quantum bit can be in a superposition of 0 and 1 at the same time. And the state, we don't know the state of this qubit until we actually measure it, in which case we collapse. And again, we're going to talk about that term a little bit more in the third lecture of the series. But in that case, the qubit has to choose to either be 0 or 1. And an example of this, of course, is the Schrödinger cat experiment, where we put a cat in a box. And this is a thought experiment, by the way. No animals were harmed in coming up with this idea. And there's some mechanism that kills the cat with 50% probability over the course of an hour. Now, Schrodinger's thought experiment was, okay, what happens if I put a cat in this box with this mechanism and I, seal the box from the outside world and wait an hour? Is the cat dead or alive? And the idea from quantum mechanics is that the cat is both dead and alive at the same time until we open the box and actually see if the cat's dead or alive. The next quantum resource that is key for quantum computing is entanglement. And again, we're going to talk about entanglement in detail also in future lectures, but entanglement is a form of quantum correlation between two objects that cannot be described using classical physics. So it's a very strong quantum correlation. For example, if I have, let's say, two spins, which some of you might have heard of, but let's say two magnets that either point up or down, and they're entangled such that, if one's pointing up, the other one's pointing down. And I send them across the universe. So I keep one on Earth, I send the other one to, let's say, the moon. And I measure the state of my magnet. That measurement, the fact that I've measured the state of my magnet, will immediately determine the state of the other magnet or spin. And this phenomenon cannot be explained using classical physics. And we're going to talk about this more during next lecture. And finally, quantum interference is another resource at our disposal for quantum computing. The idea of quantum interference kind of comes from the fact that all waves are particles and all particles are waves, and therefore particles can interfere with one another just like waves do. So the bulk of this lecture is going to be focused on the idea of wave-particle duality and how that can be, or rather that can be utilized as quantum interference for quantum computing. So these three, weird or counterintuitive rather, quantum properties enable the design of quantum algorithms which can compute in ways classical computers cannot, making quantum computers more powerful for solving certain types of problems. And again, quantum computing is an application of quantum mechanics. So I hope that this first slide serves as a motivation for why do we need to learn a little bit of quantum mechanics at least. Because by knowing quantum mechanics, we will learn about certain tools that we have at our disposal that allow us to gain an algorithmic speed up over classical computers. And the analogy that I draw with with normal classical computing is that if you know how to code, right, you can code a classical computer. But then you take an algorithms class and you find out ways to make your code more efficient and to run more faster. So we can think of quantum computing the same way. Essentially, by learning quantum mechanics, we learn about the resources that we have access to make our quantum computation faster. And again, to be able to solve problems that classical computers cannot. And I want to give you a second motivation for why do we need to know quantum mechanics. The thing is that especially nowadays in the 21st century, we don't need to know semiconductor physics to learn how to code. And our computers operate using transistors, and all of the behavior of these transistors is governed using semiconductor physics. But I personally don't know the exact semiconductor physics. I know a little bit, of course, but not everything, not definitely to the full extent, and neither do you. And you're still able to code, very successfully. You're able to code whatever you want on your classical computer. So now that begs the question: why do we need to learn quantum mechanics to do quantum computing? Well, the idea is that there's also another part to doing quantum computing. So it's not just quantum programming, but rather because qubits are physical systems and quantum mechanics describes the behavior of these systems. And some of you will end up actually developing and improving the quantum hardware that is required to do quantum computing. And for that, you need to know actually a lot of quantum mechanics, definitely more than what we're covering here. But this is just to give you guys a taste for, why are we spending 3 lectures covering quantum mechanics before diving into quantum computing. Okay, so let's get started by talking about particles and waves. So let's travel back in time before people discovered quantum mechanics. The conventional knowledge of physicists at that point was that the world is made out of particles which interact with one another, bounce off of walls, bounce off of each other. I think we have a good idea intuitive of how particles behave. And waves. And waves are, I guess, periodic structures. And we can describe waves based on frequency or wavelength. So if the distance between two peaks, actually let me try to write here, is small, that is a small wavelength. Two peaks or two valleys. Small wavelength, which means high frequency. Whereas if we have a large wavelength, that leads to smaller frequency. So the key takeaway point is that wavelength and frequency are inversely proportional. So if I show wavelength as lambda, and frequency as f, lambda is 1 divided by f. And we're going to talk about this more in detail. So maybe with that, let's move on to the next slide. So let's talk about particles first. Regardless of size, all particles have a well-defined position. So meaning that you can point exactly where they are in space. For example, I know exactly where my Apple pen is right now. It's in my hand. I know the exact location, and I'm going to be writing with it throughout the lecture. Particles are discrete, meaning that again, there's one Apple pen here, and that's about it. I can count the number of particles that I have. And when particles collide or interact, they bounce off of each other. And a good example of that is, when you're playing pool and you hit a ball with another ball, they bounce off of each other. And that interaction is very well described by the classical laws of physics that we know. And on the other hand, we have waves. So unlike particles, waves do not have a well-defined position. Waves are spread out in space in a sense. And they are continuous, right? So if you think of water waves, for example, it's a continuous wave in the water, and like it doesn't come in discrete. You can't count the number of waves because it's continuous and it goes on forever. And when waves collide, they interfere. We're going to talk about that term a little bit more. So let's look at what interference means. So the idea here is that if I have two waves interacting and their peaks match and their valleys match, the peaks will end up amplifying each other and the valleys will also end up amplifying each other, such that I end up with a larger wave. And here, this lambda here, of course, is the wavelength, just as a reminder. So the wavelength just describes the distance between two peaks or two valleys of a wave. And again, if the peaks and valleys match, they will constructively interfere, meaning that the peaks are amplified and also the valleys are amplified. Now, let's say the peaks and valleys are completely out of sync, meaning that the peak of this first wave matches the value of the second wave, and the value of the first wave matches the peak of the second wave. And assuming that they have the same amplitude, amplitude just being the height of the wave, they will destructively interfere. So we end up with a flat line. So the idea here is that when two waves interact, they can either constructively interfere, amplify each other, or destructively interfere based on the wavelength and how the waves are actually positioned in space. And this is a completely non-particle-like effect, because again, when particles interact, they just bounce off of each other. Your wave doesn't get destroyed or amplified. The particles just go in different directions. And we see interference around us all the time. For example, interference patterns form when water is passing through two slits. So in this case, you can see interference pattern here, all these are interference-like patterns. And of course, to look at a spatial slice of it, if we have waves passing through these two slits, We have some areas with no water wave. So like, over here, we see that there's no amplitude, and some areas with amplified amplitudes, which is like this region. And that is interference. So again, we said with water waves, when we have two waves coming from two different sources, some of their valleys will cancel the other one's peaks, and in some cases, the peaks and the valleys will amplify each other. And that is the concept of interference. Okay, so now let's talk about a question that was central to the discovery and the development of quantum mechanics, and that is whether light is made out of waves or particles. Well, so there's a strong case to be made that light is made out of waves. And how do we know light is a wave? Through this double slit experiment. So again, if I go back to this slide, this is the behavior that we see with water waves. We see that if we send them through two slits, they will interfere at some points with each other on the other side. And we end up seeing the same behavior when we send light through two slits. So here we have destructive interference. And of course, we have these bright spots, extra bright spots that are constructive interference. And again, you can see a more diagrammatic approach on the right. So these waves will, again, interfere, and we end up with bright spots and dark spots. Dark spots being the places that the waves destructively interfere, and bright spots being where the waves will constructively interfere. And actually what we have over here is from an actual experiment where someone shined a laser through, again, two slits, and then looked at the interference pattern on the other side. So when we pass light through two slits, it forms an interference pattern, just like the water waves do. And this goes to suggest that light must be made out of waves because it behaves like waves. But also, can light also be a particle? And there is an experiment that suggests yes, it can be. And that's called the photoelectric effect. So the idea behind the photoelectric effect is that we shine some light on a piece of metal. And if the light has too low of an energy, no electrons are ejected with low energy light. And that it doesn't matter how much we use, it doesn't matter how long we expose the electrons, which are, again, we can assume particles in this case, particles to this low intensity, or not low intensity, low energy light, nothing will pop out on the other side. Now, if I actually shine a laser light, or some light that has higher energy, again, we're not going to define what high or low energy means necessarily, but just take my word for it. Then we see that electrons are ejected with high energy light. And this doesn't make sense if light is only a wave, because low energy waves will eventually excite and dislodge the electrons in the metal. So if I just hold my light source there for long enough, something must come out. Whereas that's not the case. And again, that is fascinating in a sense, and was very fascinating to physicists in early 20th century. In fact, Albert Einstein got his Nobel Prize in physics not for relativity, but for the photoelectric effect, the theory and the experiment. Now, something else that's interesting is, let's say I have a light source with high enough energy, and I shine it on this piece of metal. If I increase the energy, it doesn't change the number of electrons that are popping out. It just changes the energy of the electrons. Whereas now if I increase the intensity, which might correspond to the number of particles of light, potentially, again, if light is made out of particles, then I see more and more electrons popping out. And again, that goes to show more evidence as to why light is made out of particles, or behaves like particles. So what if light was also made out of particles? Then it would make sense that no matter how many particles of light you use, the electron is not ejected, just if you use ping pong balls to knock over bowling pins. So that goes to say that you essentially, if light is made out of particles, you still need particles of some amount of energy, some high enough energy to be able to knock these electrons out of the metal. So now if we try with high energy particles of light, then we can remove electrons. Again, how a bowling ball can knock over bowling pins. So based on that, light, we can conclude that light is a wave and a particle. And the wave part it's very clear from the double slit experiment that we talked about, the fact that light exhibits interference patterns. And we call the particles of light photons. And you probably have heard that term in either science fiction movies or around us, like the photon torpedo, for example. So photons are particles of light. And light is made out of photons and it behaves like waves. So that motivates the notion of wave-particle duality, which states that in quantum mechanics, all objects can be described as both a wave and a particle. So we looked at light, but now let's look at a particle that behaves like a wave. Again, we saw an experiment that showed how light waves, behave as particles. But now we're going to look at an experiment that shows that particles behave like waves. So now what I want to, the experiment that I want to introduce basically is trying to answer the question of what happens if I shine electrons through the double slit. So if I repeat the double slit experiment using electrons. Now, it is very clear to us that electrons are particles, right? They're negatively charged particles that orbit the nucleus of an atom, and a lot of the properties, of the atom comes from its electrons. Now let's try shooting these electrons through the double slit, and repeat the double slit experiment with electrons. So if electrons were to behave only as particles, and we're again shooting them at a double slit screen, we expect two patterns of just straight lines emerging on the other side. And again, the location of each of these lines corresponds to where the opening is on the slit. And this intuitively should make sense, because the particles can only end up where they're allowed to pass through the double slit. And that's where the two slits are, the location of the two slits are. So if electrons are, purely made out of particles, then we expect to see two lines where the electrons went through the slits. But now when we actually do this experiment, we see an interference pattern on the other side. And again, the same way that we saw an interference pattern with waves. And therefore, we can conclude that electrons also exhibit wave-like behavior. And actually, this is something that is not just a thought experiment, but this is something that our very own Akshay observed on a daily basis almost during his PhD, and maybe even the work that he's doing right now as a postdoc. So what we have over here to the right is an actual real image of electron interference done in lab not that long ago. So you can see there's some dark spots and there's some bright spots, and that suggests that electrons interfere like waves, and therefore electrons are also waves and particles. Okay, so with that, I mentioned that all particles are waves also. And all waves have a wavelength. And again, just as a review, the wavelength is the distance between the two peaks of the wave or the two valleys of the wave. Actually, there's a formula called the de Broglie wavelength formula that allows us to calculate exactly what the wavelength of a particle is. In this case, the lambda that we have over here is the wavelength. This h is a Planck's constant, which shows up over and over again in quantum mechanics, and p is momentum. And for those of you who are not familiar with momentum is just the mass. So it's just mass the mass of an object times the velocity of that object. Good. Let me move on to the next slide. If we're made out of waves, like human beings are made out of waves, why can't my co-instructor Fran walk through walls? Well, let's take a look at that. Let's try to answer that question. So I'm going to rewrite the formula for the de Broglie wavelength, and we're going to use that formula to calculate Fran's wavelength when she's kicking a soccer ball during a game of beach soccer. So we have that lambda, the wavelength, is equal to Planck's constant times, divided by the momentum, which is just mass times the velocity. Okay, so let me calculate lambda of Fran. I'm going to rewrite the Planck's constant, and that is 6.626 times 10 to the negative 34. So the Planck's constant is actually a very, very, very small number. And it's almost a unit of the discreteness of nature. So you can think that nature is discrete on this scale. And actually, let me go back a slide so I can just pick the units up. So it's meter squared, kilograms divided by second. So this is meter squared times kilograms divided by second. And let's assume that Fran weighs 60 kilograms. I actually do not know exactly how much Fran weighs, so I apologize if I'm offending anyone here. And we're going to keep everything in SI just because the units that we're comfortable with are in SI. And let's say when she's kicking the ball, she runs as fast and kicks as fast as let's say 5 meters per second. So with that, I actually did the math before lecture, and what I end up with is that Fran's wavelength is 2.21 times 10 to the negative 36 meters. And this number is extremely small. So to put it into perspective, the Wi-Fi wavelength, the wavelength of Wi-Fi that we're used to having around us and definitely behaves like a wave, is 0.125 meters or 12.5 centimeters. And the X-ray wavelength, which is very high frequency, low wavelength, right, is of order of 10 to the negative 9 meters or 1 nanometer. But we just saw that Fran's wavelength is of order of 10 to the negative 36, which is very, 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 very small. And because of that, Fran does not exhibit the same behavior that, for example, Wi-Fi does. Wi-Fi can travel through walls, go from room to room, and you don't need to have a Wi-Fi source in every room to have internet access in your room. You just have one Wi-Fi source in the house, and the Wi-Fi signal travels throughout the house. Whereas in Fran's case, her wavelength is so small that she can't just walk through walls. So if I were to draw a diagram, let's say this, we're going higher wavelength to the left, sorry, to the right. And when we go to the left, it's lower wavelength. So as the wavelength gets larger and larger, we see more wave behavior, or more wave-like behavior rather. And as the wavelength becomes lower and lower, just like, again, Fran's wavelength when she's kicking a soccer ball, we see less wave-like behavior, or I'm going to call it more particle-like behavior. And that is why Wi-Fi, although both Wi-Fi and Fran are made out of waves, That's why Wi-Fi can pass through walls, because it has a much higher wavelengths, or rather larger wavelength. But FRAN can't walk through walls because FRAN's wavelength is minuscule. It's non-existent. So this is why we don't see this wave-particle duality in our daily lives, because at the macroscopic scales, at the scale of the objects that we see around us on a daily basis, everything behaves like a particle, because the wavelengths are so small that we can't see their wave-like behavior really. Okay, with that, I'm going to move to the next slide. And so, again, we're trying to motivate, why do we care that particles are also waves? So this assertion, this result, means that particles are not discrete and solid objects, like, what we assume that particles are. And they don't have a well-defined position necessarily at very, very small scale. So if you take a very accurate microscope to a particle, you'll actually see that there are ways to figure out that the position is not exactly well defined. But instead, their position can be described by something called the wave function. So here, this symbol psi is what we call the wave function. The x that we have over here just tells us the position, and the t is the time. So we can have a wave function for a particle at any given position at any point in time. And now, of course, the amplitude squared of this wave function gives us a probability of finding the particle in that position at that time. But the key thing is that the wave function doesn't tell you exactly where the particle is, but rather what is the probability of finding the particle at some place at a given time. Again, the wave function is used for calculating a probability cloud. So it shows how likely it is for a particle to be in a certain region of space at a given time. And we can see the example of that with the wave function of electrons. So here, these two visuals that we have here are pictures of the wave function of our favorite particle, the electron, which we've talked about extensively. They show that there's a chance that the electron will be somewhere within those regions. So these are for, of course, different electrons with different orbital energies, which we're not going to talk about, but this area is a very rich area of physics and chemistry if you're more interested in pursuing it. So again, what this wave function tells us is that we can find, for example, in this case, we can find the electron at like any point in the sphere, and it tells us exactly with what probability is the electron, in that exact location at the time that we want on the sphere. Now, where does this concept of wave-particle duality come into play in quantum computing? So let's go back to qubits or quantum bits, which are the building blocks of our quantum computer. So although qubits are physical objects, meaning that they're particles, again, a qubit can be an artificial atom, a real atom, a photon for that matter. The idea is that, although they're particles, they behave like waves, or they can behave like waves. So therefore, the superposition states of a qubit can interfere with one another, similar to the way that water waves interfere or light waves interfere. And we can use this interference to amplify the probability of getting a correct answer out of all possible superpositions, or destructively interfere them to eliminate the probability of getting the wrong answer in quantum computing. And we can use this as a tool for quantum speedup. So quantum interference, in fact, is one of the main tools in our quantum computing arsenal. And again, we're going to see that in the future when we talk about quantum algorithms. But the most notable example of a quantum speedup from quantum interference is Grover's search algorithm. Which uses a technique called amplitude amplification. which again is a fancy term for saying that we start with an equal superposition of all possible answers, and we somehow design an algorithm that creates constructive interference for the probability of getting the correct answer, and destructive interference for all the wrong answers. And then by the time we're done running our quantum algorithm, we measure our qubit, we get the right answer with high probability. And this leads to, again, this class of amplitude amplification algorithms are one set of tools at our disposal to gain a quantum speed up over the best known classical algorithms. So in essence, this notion of wave-particle duality is not just limited in studying physics and anything that comes from quantum physics, but rather it's actually something that we utilize in quantum computing for a lot of speedups. So let's discuss what we've talked about so far. We've defined what quantum means. And again, just as a refresher, quantum means something that's discrete in nature. And there are some consequences of that, of course. We went over the differences between quantum mechanics and quantum computing. And again, just to refresh the notion, quantum mechanics is a tool that we use in quantum computing. So we use some of the resources that are offered by the counterintuitive, weird nature of quantum mechanics to gain speedups for quantum computing over, again, what classical computers can do. And then we looked at experiments that proved that waves act like particles and particles act like waves. And again, that was to reinforce the notion of wave-particle duality, that everything that's around us has both a wave-like nature and a particle-like nature. Now, the reason why the objects around us act strictly as particles is because due to their size, their mass, their wavelengths are very, very, very small, such that it is not possible for us to actually see them behave like waves in the macroscopic world. Whereas, for example, an electron is actually very small, and an electron is extremely light. That's when we can see, for example, interference patterns coming out of electrons when we send it through a double slit experiment. And finally, we introduced the wave function, which again, the wave function is very similar to the amplitudes that we had in front of our qubits from last semester. And again, we'll review them in a couple of lectures. That it gives us the probability, well, rather wave function squared, of course, wave function magnitude squared, gives us a probability of finding a particle at a given position at a given time. Again, this applies for all positions in space and all times. You can assign a wave function to a particle for all of those, and you can get the probability of your particle being somewhere. And again, this might sound a little bit counterintuitive based on the fact that what we're used to is particles having a defined space. But in quantum mechanics, quantum particles actually their position is probabilistic. So they're not in one space with 100% one location with 100% probability. Some could be, but that's generally not the case. Instead, they're spread out in space, and there's you can assign a probability for finding them in different positions in space. And next, after the break, we'll mathematically describe the relationship between this wave function and the energies of the quantum state. So with that, let's take a 10-minute break, and then we'll come back. Everyone, let's get started again. But before we jump into the material for the second half of the lecture, we'd like to answer some questions.
Alrighty, Amir. Okay, so we got several really good questions. Before we jump right into that, I just want to reiterate what I shared in the chat, everyone, which is please remember that there are thousands of students in this class. And so don't overwhelm Akshay with questions. It was never an intention that you would get every single question answered in real time. So use the other online resources available so we can only ask questions that are relevant to what Amir is teaching. Several students asked things that he was going to answer in the course of the lecture anyways. So please be patient, and we appreciate you respecting Akshay's hard work here. So with that, let's answer some of the most common questions. Amir, at the beginning, you said something about doubly discrete. Can you clarify what you mean by that?
Yeah, so I'm not exactly sure, what was the context. So we have the double slit experiment.
How about
which again we have
like discrete
sorry
in the context of a particle?
Yeah, so I mean, yeah, and also okay, so yeah, there's a double slit experiment which exhibits the wave-like behavior of particles or waves for that matter, but then particles act discrete. Now, I think where that question might be coming from is when we shine electrons at the double slit experiment, what we expect is to see two line patterns on the other side. Each, if the electron was completely a particle, completely behaved like a discrete particle. And again, each line corresponds to the location, the position of where where one of the slits are. But in reality, what we see on the other side is that we see an interference pattern, which goes to suggest that electrons actually do behave like waves and not purely particles.
Cool. And if you're feeling confused by double slit still, a large part of lab section this week will involve going through the details of it further. So just be patient and your question should be answered. Another question was, what would Fran's wavelength be if her velocity was 0? What if she was traveling really fast? Could she pass through walls then? So if you play with
so that's a good question, and maybe let me. I'm trying to decide which one I want to address first. So maybe let's look at the case where Fran is moving too fast first. So again, just as a review, lambda was equal to h divided by this h being the Planck's constant divided by mass times velocity. So as velocity goes up, which is the case that Fran starts running really fast, the wavelength will actually go down because again, based on this relationship, the wavelength is proportional to 1 over velocity. So in fact, as Fran starts going faster and faster, she starts exhibiting particle-like behavior more and more instead of less. So now the question is, okay, what if Fran's velocity is absolutely 0, right? The opposite, because, based on this, if the velocity is actually low, there is a chance that this lambda gets larger as velocity goes lower. But now I wasn't planning on talking about this in lecture, but I think, this principle of quantum mechanics does a great job of explaining this question, the answer to this question. And that is that's called the Heisenberg uncertainty principle, named after Werner Heisenberg and not the guy from Breaking Bad. And what Heisenberg's uncertainty principle tells us is that if I look at the uncertainty in x and I multiply it by the uncertainty in momentum, which again in this case is mass times velocity. So let me just write this as the uncertainty of, or rather, mass times the uncertainty in position times the uncertainty in velocity. this will be larger than h, which is again Planck's constant that will keep on showing up, divided by 4 pi. Now, what is the significance of the Heisenberg uncertainty principle? So now what this tells us is if I precisely know the position of something, then I have no idea about its velocity. Because, as this uncertainty in position goes up, or rather in this case down, uncertainty in velocity goes down, and then let's look at the vice versa. As uncertainty in position goes down, the uncertainty in velocity goes up. So if I let's look at the second case. If I exactly know the velocity of a quantum object, which is having this small uncertainty, having delta v. So let me write this maybe. If I exactly know the velocity, translates to an uncertainty in velocity that's 0, right? So if I exactly know the velocity of something, I'm going to have no idea where the position is, because this uncertainty in position has to go to infinity. And this is another part, another intuitive part of quantum mechanics, that if you know one property of the system, the velocity, you're going to have no idea what the position is. Or if you know exactly where the position is, you're not going to have any idea where the velocity is. So let's say we say that Fran's velocity is 0, exactly 0, then we have no idea where Fran is in space. Fran could be on Earth, could be on Mars, could be in another galaxy for that matter. And also vice versa. Like if I say that I exactly know the position of Fran, like where Fran actually is, I have no idea where what Fran's velocity is. But now, of course, the idea is that this effect is kind of small, because again, this h bar is a number that's of order of 10 to the negative 4, whatever units. So we don't see the effects of the uncertainty principle in our everyday life, just because again, things that we're looking at are so large. That they don't break the uncertainty principle with the tools that we have to measure. So for example, you can see the position of something, like you can see the position of my pen, and I know that it's not moving as far as I can tell. But the atoms in the pen are probably moving, are probably wiggling around a little bit. So that is not something that I can see with my eyes. So that's why real life doesn't violate the uncertainty principle, but Fran's velocity in a quantum world when she's passing through a wall can never be 0, can never be exactly 0, because then who knows where she is? She might not be even near the wall. But the idea behind that question's correct in a sense. So for larger objects, as the velocity gets smaller, the wavelength gets larger. But in order for, I think, Fran to be able to move through a wall, she needs to go as slow as, I'm guessing, Fran. Okay, so let's see. Okay, so V of Fran to pass through walls should roughly be of order of 10 to the negative 30 meters per second. And at that speed, it'll take her more than the age of the universe to get through the wall. So again, this is why the classical intuitive world around us doesn't break when we introduce quantum mechanics. Because although the laws of quantum mechanics are there, we're at such large scale, we're such large scale objects for quantum mechanics that these counterintuitive effects don't actually affect our day-to-day life.
Cool, Amir. A related question, why can long wavelengths pass through walls?
Why can long wavelengths pass through walls? Well, so at the end of the day, the walls are made out of molecules and atoms. And what happens is that if the wavelength is long enough, it can pass through, like your Wi-Fi, for example, it can pass through the material of your wall because there's a lot of empty space in there. Of course, that that the answer to that question is a little bit more complicated because on one hand, it depends on the wavelength of your wave. It'll depend on the material of your wall. So, for example, if you have a wall that's purely made out of metal, let's say iron, Wi-Fi doesn't actually pass through it. But those are the subtleties. The general thing is that it can pass through the material, the seams of the wall, in a sense.
Cool. Two more questions. So a lot of questions about superposition and interference. Specifically, is there a difference?
Yes. Yeah. So actually, maybe, and I think that might answer another question that I saw posted. So superposition is a phenomenon in which a quantum particle can be in two places at once. And actually, superposition, in a sense, if you really want to get technical, is a consequence of wave-particle duality. Because as we mentioned earlier, waves can be. Waves are not necessarily at one specific region in space, but they can be, in multiple regions at once, and it's hard to tell exactly where they are. Now, if a particle has wave-like behavior, it's also natural to assume that it could have an uncertainty in its position, which gave rise to the notion of a wave function. So superposition, again, just to reiterate, is when a quantum object is in two places at once, or we refer to it as being in two states at once. Whereas interference is how waves behave when they collide and they interact. Now, of course, quantum particles in a superposition can interfere with one another. And in fact, the interfering of quantum superpositions is what leads to quantum speedups in quantum computers. But they're very different concepts, I would argue.
Hey, Amir, just to give us a quick visual, can you sketch something that kind of describes those relationships?
Interference and
versus superposition.
These are hard things to visualize, I have to say. So maybe let's borrow an example from last semester. So when we have, I'm going to talk about qubits, and for those of you who are joining us now, hopefully you have had a chance to familiarize yourself with the material that we've already talked about. And if not, we're going to be going through this again and again and again. This is the name of the game when you're doing quantum computing. But let's say now I have a qubit that's in a superposition of 0 plus 1, right? And I'm going to call this psi. So this is called a superposition. Again, I can be in two states at once until I measure. Now, let's look at a case for interference. So let's say now I apply this Hadamard gate to psi. And we've talked about this Hadamard gate before, but if I apply it to 0, it gives me a superposition of 0 and 1 again with 0 plus 1 divided by square root of 2. And if I apply it to 1, it again gives me a superposition, except for that this time there's a minus sign in between, divided by square root of 2. Now, if I apply this Hadamard to psi, again, based on the concepts that we learned about quantum operations, the gate, the operation will apply to each part of the superposition separately. So I get an h applied to 0 plus an h applied to 1 divided by square root of 2. Okay, so now let's break this down. So now I can break this h times psi to two parts. So the first case is when we apply an h to the 0 state, right? I have the h applied to the 0 state gives me a 0 plus 1 divided by 2 because there was a square root of 2 here and a square root of 2 here. So I multiply these two together and I get a 1/2. And now if I apply this h to the 1 state, I get 0 minus 1 divided by square root of 2. And of course, what I had is that I had to add these two together. Now, when I add these two, the probability of getting 0 from the top line, which is when we apply the gate to the first part of the superposition, actually adds up with the second part. So I end up getting 0 with 100% probability, and that's constructive interference. Now here, the probability of getting a 1 will destructively interfere because we have, +1 here and -1 here. So these two will cancel each other out, and that's called destructive interference. So here in this example, we covered what superposition is, again, in terms of quantum, state of a qubit and operations that we're familiar with. And we talked about, how does quantum interference come into play when we do quantum computing? So yeah, hopefully that was sufficient.
Cool. And we'll definitely come back to it. Last question before you jump right back in. Someone asked, why do we say quantum mechanics is weird? So maybe you can summarize everything you've said up to now and why we use that word weird to describe it.
And I try to refrain from using the word weird. Rather, I say counterintuitive, which means the same thing. But if you think about it, in our daily lives, we're not used to particles being waves, right? I mean, you're either a particle, you're either a peanut, let's say, or a Wi-Fi wave. You're not both. You're one or the other. That's the common knowledge, from the classical world. Or an object has a well-defined position. You can't be in two positions at once. I'm either sitting in this room or I'm sitting in the kitchen. I can't be in both places at once. Whereas in quantum mechanics, something that we discussed is that both of these are actually real phenomenon that can be observed in lab on with proper tools. So that's why we say that quantum mechanics is counterintuitive. It's because some of the things that we see because of quantum mechanics and in the quantum mechanical realm is different than what we expect based on our daily life experiences.
Cool. Let's keep going and see even more about how it's so weird.
Yeah. Thanks, Rachel. So let's see. So now again, let's go back to the discreteness problem, or the proposition that we have. So we know that the wave function describes the probability of finding a particle somewhere in space. That's what we introduced in the previous part. But now we can use this information plus something called a Hamiltonian operator. And let me maybe underline that. We'll come back to that. To find the allowed energy states of that wave function. So again, let's look at the example of stairs versus a slide. So in the quantum world, which is like the stairs, you can only be at specific, specific heights from the ground. It's basically wherever your steps are. Whereas when you're on a slide, you can be in a continuous set of positions from the ground. So your height, the height that you have from the ground, can be continuous in the case of a slide, whereas in the case of stairs, it's actually discrete. And again, turns out that when it comes to energy, energies are also discrete. Like the energies that a well-defined quantum wave function or quantum state can have is discrete. So you can only have certain values of energy and nothing in between. And again, that is also a little counterintuitive classically. The fact that nature is discrete rather than continuous. So a Hamiltonian is a quantum operator that gives us the energy of a quantum state. And again, if you guys remember from previous semester, quantum operators can be treated as objects that tell us properties about our quantum states. So for example, momentum, I mean, of course, there's some special cases they need to Hermitian, and we're going to talk about that more. But for example, there is a position operator that gives us that tells us the position of a quantum particle. Or there's a momentum operator that tells us, what the momentum or mass times velocity of a particle is. Well, similar to those two operators, there's also this other operator that we call a Hamiltonian that tells us what the energy of the quantum state is. And the way that we show it is this Hamiltonian operator multiplied by a quantum state gives us, so this is a scalar, this is just the energy times the quantum state. And as a bit of a review, so if you guys remember from the first semester, we talked about eigenvalues and eigenvectors. So the eigenvalues are the allowed outputs or solutions rather to an eigenvalue equation. So we're using the Hamiltonian operator in an eigenvalue equation to find the allowed energy states of the wave function. And again, just as a refresher, so if I have an operator A, V is an eigenvector or an eigenstate. You can call it either or. If A times V gives me back V, the same vector, times some scalar in front. So the scalar is called an eigenvalue and V is called an eigenvector of an operator A. Now, talking in quantum mechanical terms, here H, the Hamiltonian, is our operator. This psi is our eigenstate. And then the energy is the eigenvalue, or again, sometimes we refer to them as eigenenergies. It comes from the fact that they are energies. And the idea is that because of the properties of the Hamiltonian, these energies are well defined and discrete. So, before we talk about quantum energy equation or the Hamiltonian, let's talk about the classical energy equation. So something that I remember from the physics classes I took back in high school is that total energy is equal to kinetic energy plus potential energy. So kinetic energy is the energy that you have based on how fast you're moving, whereas potential energy is an energy that you have stored based on, in the case of a roller coaster, how high up you are. And the idea is that because when you fall, you'll have a lot of energy. So the higher you are, if you fall, the faster you'll hit the ground. But you're not necessarily moving, so it's potential sort of. So let's look at an example. Let's say I want to look at the example of a particle, a ball, let's say, that is moving with speed velocity v rather, has mass m and is at distance x from ground. Well, what is the energy of this ball? Okay, so again, something that a lot of us have seen in high school is that energy is equal to 1/2. And maybe actually let me take a step back from that before even writing that form. Maybe I will just repeat what we had. Oh, and I realized that I'm using red. So energy is equal to total energy is equal to the kinetic energy plus the potential energy, which I'm just going to show as V. So now this kinetic energy, in this case, if I have a ball of mass m that's moving with velocity v, is 1/2 m times v squared. And here I have a potential that depends on the position from the ground. So let me write a note here. So this is potential energy. Can't mess that up. So I'm going to say potential as a function of position, because that is what's happening effectively. The higher up I am, the more potential I have. So if x is larger, my potential is larger. And actually in this case, so for the ball example, my v of x is just equal to m, again, the mass, times g, which is the gravitational constant, times x, which is the position. So that's how I can write the energy equation, the purely classical energy equation for this ball. Now, I want to, for reasons, I would like to rewrite this equation a little bit. So I know that P, which is the momentum, is equal to m times v. And again, maybe I'll write a note here. and this is small, this is large v, maybe let me just clarify that. And this v is velocity. And okay, so then in this case, then if this is the definition of momentum, then p squared or momentum squared is going to be equal to m squared times v squared. I just squared both sides. So I can rewrite my energy now as p squared divided, so this is 1/2 mv squared. Here I have m squared v squared. Base for the value of p squared, momentum squared. So I can write this as p squared divided by 2m, and then plus whatever the potential is. And the reason why I'm keeping this potential general is because we could have the other potential terms included in there. For example, if you have a charge near a like let's say two charges near each other, there's some potential energy in there. So if the charges are the same, like the same sign, so if you have two positive charges, they'll repel one another. If you have two negative charges, they'll also repel one another. Or if the signs are different, they'll attract. So this V, I'm just keeping it general. In this case, again, in this case, when we're talking about a ball at a certain distance from ground, it's equal to mgx, but could be anything. So now let's talk about the Hamiltonian form. So we need a Hamiltonian that captures different ways a quantum system could have energy. And that, in a sense, comes from the classical energy equation. Yeah, let's look at another example. Let's take the example of an electron around a nucleus. Yeah, the total energy is going to be the kinetic energy plus the potential energy. In this case, the kinetic energy of the electron is, again, how fast the electron's moving. But now the potential energy, which is the stored energy, is no longer from gravity this time, unlike the previous example, but it's how far the negative electron is from the positive nucleus. So that determines the potential energy in this case. And that's why I left the potential as a general thing in the other case. So how can we go from an energy equation to Hamiltonian? Well, there's a formal tool for it that I'm not going to talk about in this lecture. In fact, it's something that you'll cover in an undergrad physics degree. But we're going to do it another way, hopefully a more intuitive way. So let's look at the example again from what I had in two previous slides. That E, the energy, is equal to momentum squared divided by 2 times mass. Again, this is the same as 1/2 mv squared that we're all familiar with. Plus, some potential V that depends on X. So now what I do is that I will map the momentum of the system to a quantum momentum operator. Which I will show as P hat. And what this really means is, this is an operator that if I apply it to a quantum state, it tells me it returns the momentum of the quantum state. So maybe let me write that. Okay, so hopefully that should be clear. And again, the idea is that at the end of the day, by applying this momentum operator, we want to be able to get the momentum out such that we can plug it into our energy equation. Now, there's another part to this too, right? There's this X. So that I also want to map the position to a quantum position operator. Yeah, I showed this as x hat. The hat tells me that it's a quantum operator. And here again, it's the same description. I will write it again for completeness. So if I apply this operator to a quantum state, it tells me now the position of that quantum state. Now, using these two tools, or rather these two operators, I can map my energy, my classical energy, into a quantum operator. So here, E, which is the classical energy, goes to H, which is the Hamiltonian now, the quantum operator for energy. And I can write that as operator P squared 2m plus V, again, this X here is going to be an operator. And hopefully that should be clear. Again, just P squared, the operator P squared is similar to applying two P operators back to back. So I can also rewrite this as operator P times operator P divided by 2m plus then the potential, the operator, the part that gives me the potential energy of my Hamiltonian, or of my energy, total energy. Again, so this goes to reiterate that this Hamiltonian operator that we talked about is an operator that when I apply to a quantum state, it tells me the energy of that quantum state. And based on the laws of quantum mechanics, there are only certain values of energy allowed for any quantum state. So that brings us to the Schrödinger equation, which describes how the wave function changes in time based on the Hamiltonian, or based on the Hamiltonian of the wave function. And again, of course, it was derived and introduced by Erwin Schrödinger, who we have the picture of in the right, one of the fathers and founders of quantum mechanics. Now, a translation of the Schrödinger equation, is as follows. It describes how the quantum state, which for all we care about is the state of a qubit, changes in time based on its allowed energy values. And this is what the Schrödinger equation looks like. So if you're anything like I was back in high school, this might, at first sight, this equation might be a little bit intimidating. So we're going to break it piece by piece. And again, we're not going to do any complicated calculations with this. That's for an intro quantum mechanics course, like a full-blown intro quantum mechanics course. But it's good to have a general idea of what the equation is telling us and why do we care, which we're going to talk about in our future slides. So first part, this I that we have here is just the imaginary number. It's I is equal to square root of -1 as a review. This H that we have is just the Planck's constant. And in fact, we have H divided by 2 pi, which sometimes, we refer to this whole thing as H bar. So if you see H bar in the quantum literature, it's just the Planck's constant divided by 2 pi. And it's referred to as a reduced Planck's constant sometimes. Now, for those of you who haven't taken calculus, the SNCC symbols might be a little bit more unfamiliar. What this tells us, this d divided by dt, it tells us the rate of change of whatever we're applying it to, in this case psi, with respect to time. And actually, I realized that I should probably erase this. So again, here this is h bar. So what this is telling us on the right-hand side is that the rate of change of this quantum state or a wave function with respect to time is governed by the Hamiltonian, which is the operator that gives us the energy of a quantum state, times a quantum state. And this is in a sense fascinating because when we think of quantum mechanics, chances are we think that we're talking about a purely random system, that quantum mechanics is governed by randomness inherently. Whereas with the Schrodinger equation, we have a deterministic equation that tells us how this quantum state changes throughout time. And the randomness only enters when we're measuring the quantum state in an arbitrary axis. And to me, this is the fascinating thing that I want you guys to take out of the Schrodinger equation, is that the way that quantum states actually evolve in time or change in time is deterministic, and it's determined based on the Hamiltonian, or again, the operator that gives you the energy of those quantum states. But rather, the randomness enters when you're actually trying to measure this quantum state, when you're trying to collapse a superposition. With that, let's move on to why do we care about the Schrodinger equation. So the Schrodinger equation tells us how our quantum hardware behaves. Because at the end of the day, when we're thinking of a quantum computer, it is a device or piece of hardware that's made out of quantum bits, which behave based on the laws of quantum mechanics, hence the Schrodinger equation. So in a sense, it tells us how to operate our quantum hardware to get the quantum computation tasks that we want to. It also allows us to engineer and implement quantum gates. So all the quantum gates that we're going to be talking about in abstract in this course are actually implemented using the Schrodinger equation, or rather using the guiding principles of the Schrodinger equation on the hardware. And finally, there are many more applications outside of quantum computing in physics and chemistry. And having an understanding of these applications, especially in chemistry, can help us design more efficient quantum algorithms to solve chemistry problems. Again, as we know, or we've told you so far, and we're going to reiterate this, chemistry simulations are challenging tasks for normal computers because at the molecular level, everything behaves based on the laws of quantum mechanics. And with every electron that you add to the system, the number of states that you have to simulate, the number of possible superpositions that you have to simulate doubles. So that's why the largest molecule that's been completely simulated using the most advanced supercomputers out there in the world today is something around 40 to 50 electrons, which is not that complex when you think about it in the grand scheme of things. So with that brings us to the end of this lecture. I think we're going to take some more questions now, but besides that, thank you guys so much for your time.
All right, I'll invite Akshay if you have anything that stands out to answer.
I think a lot of students had a question about what the I in the Schrodinger equation is, like, what does that mean? The fact that there's the imaginary unit in the Schrodinger equation.
Oh, that's another beautiful thing about the Schrodinger equation, actually, because if we look at any similar classical equations, that I isn't there, that imaginary number isn't there. And that I, in a sense, goes, it results in the time evolution of a quantum system to be reversible. So if you guys remember from the first semester, what reversible means is that if there's an operator or an action that happens, there's another operator or action that counters the effect of the first operator. So in terms of time, you can move time. Time goes forward. You can go from time 0 to time 1 to time 2 to time 3. But what this tells us is that there is a way for us to reverse time back, to go from time 3 to time 0. And that imaginary, one of the first consequences of that imaginary number that I can think of is the fact that the way that quantum systems evolve in time is reversible. So anything that happens to a quantum system, you can essentially rewind and take your quantum system back to how it was initially. Actually, that's one of my PhD projects, actually. So for one of the projects, we're letting a quantum system evolve in time, and then we reverse time in lab and retrieve all the quantum information from that qubit of like from that initial qubit, which is quite fascinating to actually see it happen in real life.
Amir, did you want to mention anything else about quantum field theory or kind of introduce that at a basic level?
Well, I did not want to, but now that you brought it up, so one of the questions that we got is, what happens when quantum mechanical objects move near the speed of light? And of course, and then you have, in a sense, two competing forces. One of them is quantum mechanics, because you're talking about quantum objects. So like, forget about like me moving close to the speed of light. That's just going to be governed by special relativity, which is the other thing that comes into play. So for an electron moving near the speed of light, you have, again, two competing theories. There's quantum mechanics and there's special relativity. And now what Rachel mentioned, which is quantum field theory, is a unification of special relativity, which again describes how big objects move near the speed, how big objects behave when they're moving really fast, with quantum mechanics, which talks about how small objects behave. So quantum field theory describes, in a sense, how small objects behave when they're moving really fast. And again, it's a course that you take usually either in grad school or towards the end of your undergrad that is done after you complete a series of quantum mechanics courses. So it's a bit more advanced.
Cool. Akshay, feel free to jump in with questions too. In the meantime, Amir, can you remind us what a Hamiltonian is? There's several questions about that.
Yes, I'm just gonna, let me try this. Maybe I'll just leave it on that slide. So a Hamiltonian is a quantum operator that gives us the energy of a quantum state. And again, the analog that I drew is that there is a position operator that tells us the position of a quantum state. And there's also a momentum operator that gives us the momentum of a quantum state. So Hamiltonian, you can just think of it as an energy operator. That's how I would describe it. And again, energy is an observable property of the system, so it's something that I should be able to extract.
Okay, I'm just scrolling through questions. Anything else, Akshay, from you?
I think some students were confused about what exactly the hat means above the
That's a great question. So the hat just means that it's a quantum operator. And actually that is something that I repeat here, for example, right? So we have classical momentum, and when we want to construct a momentum operator, we put a hat on top. Or classical position, and when we want to turn that into a position operator, we put a hat on top. So maybe I will add that as a note to this slide. So maybe this is a bad color now for the slide. Okay. So this H hat, so that the hat indicates a quantum operator. And of course, some papers do end up dropping the hat when you look at more advanced quantum computing or quantum mechanics papers, but usually from the notion, it's really clear. And for at least at the introductory level, I highly recommend keeping the hat, because it helps you guys clarify what's a quantum operator and what is a classical variable.
Okay. I guess we're just getting into some review concepts, but these are really foundational, so they're good questions. Amir, let's break down some jargon. So people are asking, what do you mean by an operator? Is that a gate? Like, what is the analog to it? And also a pretty basic question, but an important one, what do you mean by quantum state?
Okay, we will talk about these more and more, and we've already like spent a couple of lectures on them. But a quantum state is, you can think of it again in the context of quantum computing as a vector that describes the state of a quantum system. So let's think about our qubit. For example, the quantum state of a qubit can tell us, if the qubit is in the 0 state, in the 1 state, or in a superposition of both. And if it's in a superposition of 0 and 1, is it 0, or sorry, is it like, 0 50% of the times, 1 50% of the times, or is it 0 25% of the times and 1 75% of the times? So that's what a quantum state is. Again, it's for our purposes, we can think of it as a vector that describes the state of a quantum particle, in our case, a qubit. And an operator is, you can think of it as a matrix from the first semester that changes a quantum state such that it maps, your initial quantum state to some other quantum state. And again, we're going to have a more visual representation for quantum states and quantum operators, at least for a qubit, in a couple of lectures when we introduce the block sphere.
Okay, anything else from you, Akshay? Otherwise, I guess we can end a little bit early. Before we do, Amir, if there's anything more you want to say about your research or just like help bring this to life for us, what researchers are doing with this information, kind of how it's been transformative to the field.
Oh, absolutely. I'd be more than happy to talk about that. And maybe, so I want to especially emphasize the Hamiltonian and the Schrodinger equation. So the Hamiltonian of a system plays a very important part in the questions that I have to answer in research. So in my research, again, I work on superconducting qubits, which are artificial atoms. And the system, these artificial atoms can be described using a Hamiltonian, again, based on what the energy of every individual qubit is and how they interact with one another. So all that information is in a Hamiltonian. So when I get a Hamiltonian, I can, using the Schrodinger equation, I can figure out exactly what happens if I let my system sit idle. Because again, the quantum state of a system will, and maybe I'll go to the Schrodinger equation slide, the quantum state of a system will evolve based on this Hamiltonian. That again, I know what the Hamiltonian is, so I'll have a general idea of how the system will evolve. Now, let's say I want to do a quantum gate. I want to perform a quantum gate on the system. Well, then I can introduce a microwave drive, for example, that adds another term to this Hamiltonian. And then since I have the Schrodinger equation, I know exactly how that extra term that comes from, an engineered gate that I want to engineer will affect my quantum state. So I can play with the parameters that way, and somehow using again the Schrodinger equation get the gate that I want in experiments. So for example, if I want to flip a qubit from 0 to 1, the Schrodinger equation tells me what like how I need to drive my qubit for how long with what microwave amplitude to get the transition that I want, again, to flip a qubit from 0 or 1 or from 1 to 0, which is called the next gate. Something else that I'm interested in my research, the work that we're publishing right now actually is to figure out how quantum systems evolve in time, or complex quantum systems evolve in time using a quantum computer. Now, the motivation behind that is when we're trying to design better material or like new superconductors or semiconductors, a lot of these simulations, simulating the quantum properties of the material is actually very difficult for a classical computer to do, for the very same reason that classical computers can't simulate molecules. So it makes sense to try to think of ways to actually do this with a quantum computer. Again, the overall goal is that by getting a better insight into the physics, underlying physics of the material using a quantum computer, we can design better quantum computers for the future, but also better nano devices and advanced nanotechnology and things like that. Essentially gain knowledge that we don't have right now with our current computing technologies. So to that end, something that I'm interested in is not only how a quantum particle moves around. If I put it in let's say a lattice, like a metal, for example, a conductor, but rather how does quantum information propagate? And again, we're going to talk about the difference a little bit in future lectures. And for that, like something that we do actually is we start by letting a quantum system evolve using the through the Schrodinger relation, through the Schrodinger equation, based on the Hamiltonian of the system, which is again the energy equation of the system. And then we play some smart tricks to reverse the time evolution. So let's say you have a let's say you have a bottle of perfume, right? And then you kind of puff some out. And then, as things evolve, this perfume will disperse in space. And now we have a way to actually reverse time and get all the perfume molecules back in the bottle. So that is effectively one part of what I do. And of course, quantum particles propagate a little differently because of interference and stuff like that. And maybe I can talk about that a little bit more later. Like how do we actually see the effect when you have a quantum particle propagating versus a classical particle propagating? And again, it turns out quantum interference actually makes quantum propagation much faster. And that leads to many other cool applications, of course, I don't want to get into. But the idea is that we can use these tools, again, based on the last half of this lecture that we talked about, to really understand nature better, in a sense. And based on that, engineer better material, better nanostructures, better molecules, better medicine, things like that. So I think that's a part about these last few slides that I find the most fascinating, at least. And hopefully you guys do too. Again, it's something that I'm passionate about and I've been spending a good portion of my past 2 years on. Yeah, any more questions, Rachel? Or anything specifically they want me to talk about?
Yeah, I think we can probably time maybe ever end early, but thanks Amir for getting us excited about quantum mechanics. Just to reiterate, if anyone's still feeling used, a lot of this, to use Amir's word, is counterintuitive. So you'll go through in lab sections this week. So just be patient, and we have 2 more weeks of this as well. So thanks Amir, thanks Akshay for all of your hard work answering questions.
And Rachel, I want to reemphasize something. So we are going to see these concepts from quantum mechanics in action when we do quantum computing. So even if it's not clear during this first pass, we are going to do concrete examples of it, and you'll become more comfortable with it. Because again, I remember when I was learning about these back when I was an undergrad at MIT, in the first pass, it seems very abstract, and you wonder, why this is ever useful. But as you, again, for quantum computing especially, as you start doing quantum computing, you start seeing these concepts making a comeback in more and more concrete ways. And that repetition, I feel like, will rather emphasize learning in the future, but also it'll make, the things that we're talking about now more clear if you go back and visit them at the end of the lecture. Or not at the end of the lecture, but rather the end of the course.
Just like all the math from last semester, right? Students can
exactly
back. Yep. Exactly. Cool. Well, thanks for everyone's kind comments, and we'll make sure Kira gets the happy birthday wishes. We're not going to do a photo. It's too logistically complicated with this many students. But share your photos with us on Twitter from you watching lecture, and we'll amplify those. Cool, guys. Have a great week. See you in lab, and then see you next Sunday.
Thank you, everyone.